Partition of a sample space. Hello everyone. Today, we are going to dive into a fundamental concept in probability theory called the partition of a sample space. Now, as you progress in your studies, especially as we begin preparing for more complex topics like Bayes' theorem, you'll find that working with a massive, complex sample space can be quite overwhelming. To make things easier, we need a way to break that large space down into smaller, more manageable pieces. This specific process of dividing our total set of possible outcomes into these distinct, organized parts is exactly what we call a partition of a sample space. In the upcoming slides, we will look at the specific rules required to make such a division valid. Understanding the concept. Now that we've introduced the topic, let's dive into what this concept actually means. First, we need to be clear on what a sample space is. When we talk about a sample space, denoted by the capital letter S, we are referring to the complete set of every single possible outcome that could occur in a random experiment. Think of it as the big picture or the entire universe of possibilities for our study. So, if we want to perform a partition, what are we actually doing? You can think of a partition as a way of slicing this large sample space into several smaller distinct events, which we can label as E sub 1, E sub 2, and so on, up to E sub n. The key here is the precision of these slices. Every single possible outcome from our original sample space must fall into exactly one of these events. There can be no outcome left behind, and no outcome can be stuck in two slices at once. As we move into the next few slides, we will look at the specific mathematical rules we must follow to ensure our slices truly form a valid partition. Conditions for partition. Now that we understand that a partition is essentially slicing our sample space into smaller parts, let's look at the first essential rule we must follow. This is condition 1, which we call pairwise disjoint. In plain English, this means the events must be mutually exclusive. Think of it this way: no two slices of our partition can overlap. There can be no shared territory between them. In other words, no two events can happen at the same time. If we want to express this mathematically, we say that for any two different events, E sub I and E sub j, the intersection of E sub I and E sub j equals the empty set, provided that I does not equal j. This notation is just a formal way of saying there is no common ground between them. To put this in very simple terms, if a specific outcome falls into our first slice, E1, it is strictly forbidden from appearing in E2, E3, or any other event in our set. Each outcome must have its own unique, separate home. Conditions for partition, continued. Now that we have established that our events cannot overlap, meaning they must be pairwise disjoint, we need to address our second essential requirement, the condition of being exhaustive. Think back to our previous slide where we talked about slicing the sample space. If we only take a few slices out of a cake, we haven't really described the whole cake, have we? Similarly, for a set of events to be considered a partition, they must cover the entire sample space from start to finish. This means there should be no possible outcome within our sample space, which we call S, that is left out or left behind. Every single outcome must belong to at least one of our events. To express this mathematically, we look at the union of all our events. We write this as E sub 1, union E sub 2, all the way up to E sub n, and we state that this union equals S. In plain English, when you combine all these individual pieces back together, they must perfectly reconstruct the original, complete sample space. If even one tiny outcome is missing, our partition is incomplete, and we cannot move forward to more complex theorems like Bayes' theorem. Conditions for partition, continued. Now that we have established that our slices must not overlap and must cover the entire sample space, there is one final, crucial rule to consider. This is our third condition for a partition, non-zero probabilities. Essentially, this means that every single event we include in our partition must actually be possible. Each event must have a probability greater than 0. If we look at the mathematical notation here, we express this as the probability of E sub I is greater than 0 for all I, starting from 1 up to n. Now, you might be wondering why this is necessary, as it sounds like a bit of a technicality. The reason is that we are building the foundation for more advanced topics, specifically Bayes' theorem, which we will cover later. In those formulas, we frequently find ourselves dividing by these probabilities. As you know from your basic algebra, division by 0 is undefined. Therefore, to ensure our mathematical models remain functional and valid, every event in our partition must have a real, non-zero chance of occurring. With these three conditions now complete, let's move away from the theory and look at some real-world examples to see how this works in practice. Real-world examples. Now that we have established the theoretical rules for a partition, specifically the need for events to be disjoint, exhaustive, and have non-zero probabilities, let's move from abstract math to a concrete real-world example. Take, for instance, a standard deck of playing cards. In this scenario, let's define our sample space, which we will call S, as the entire set of 52 cards in the deck. To create a partition, we need to slice this sample space into distinct groups. We can do this by using the four suits. We will define our first event, E sub 1, as all the hearts, E sub 2 as all the diamonds, E sub 3 as all the clubs, and E sub 4 as all the spades. As we will verify in the next slide, this grouping perfectly satisfies all the conditions of a partition we just discussed. Real-world examples continued. Now that we have introduced our first example using a standard deck of cards, let's walk through a step-by-step verification to prove that these four suits actually constitute a valid partition. First, let's check the condition of being pairwise disjoint. Think about the physical card in your hand. It is impossible for a single card to be both a heart and a spade at the same time. In mathematical terms, this means the intersection of event 1 and event 2 is the empty set. The intersection of event 1 and event 3 is also the empty set, and so on for all combinations. There is simply no overlap between these groups. Second, we must ensure the partition is exhaustive. If you look at the entire deck, every single card must belong to one of these four suits. There is no such thing as a suitless card hiding in the deck. Therefore, when we take the union of event 1, event 2, event 3, and event 4, we perfectly reconstruct our entire sample space, S. Finally, we need to verify the non-zero probability condition. In a standard deck, each suit contains exactly 13 cards. This means the probability of event I, which is 13 divided by 52, simplifies to 1/4. Since 1/4 is clearly greater than 0, this final requirement is satisfied. By passing all three tests, we have mathematically confirmed that the suits of a deck of cards form a perfect partition of the sample space. Real-world examples continued. Now that we have looked at the deck of cards, let's move away from games of chance and look at a more practical, industrial application. On this slide, we have example B, which involves factory production lines. Imagine a factory where every single light bulb produced comes from one of three different machines. We can label these machines as Event 1, which is Machine A, Event 2, which is Machine B, and Event 3, which is Machine C. In this scenario, our sample space, represented by the letter S, is simply the total daily output of all light bulbs produced by the factory. As we will see in the next slide, we are going to use these three machines to see if they satisfy our three conditions for a partition. Real-world examples continued. Now that we have the scenario for our factory production line, let's perform a step-by-step verification to prove that these three machines actually form a valid partition. First, let's check the condition of being pairwise disjoint. In this context, think about a single, specific light bulb coming off the line. That bulb was manufactured by exactly one machine, either machine A, B, or C. It is physically impossible for that same bulb to have been produced by both machine A and machine B at the same time. Because there is no overlap between the groups, we satisfy the first rule. Second, we must ensure the set is exhaustive. This means we can't have any missing bulbs. In our factory, every single bulb in the total daily output must have come from one of our three sources. Machine A, Machine B, or Machine C, there are no mystery bulbs that don't belong to any of these machines. Therefore, the union of these three groups perfectly reconstructs our entire sample space. Finally, we look at the non-zero probability condition. As long as all three machines are up and running and actually producing bulbs, the probability of picking a bulb from any specific machine is greater than 0. We need this to be true so that, as we will see in our upcoming lessons on Bayes' theorem, we don't run into any mathematical errors like dividing by 0. So, since all three conditions are met, we can confidently say that machines A, B, and C create a perfect partition of our production output. Mathematical examples of partitions. Now that we have explored how partitions work in practical, real-world settings, like playing cards or factory production, let's shift our focus to the more abstract side of probability. Sometimes, we aren't looking at physical objects, but rather at pure mathematical sets. Our first abstract example is something you are likely already very familiar with, an event and its complement. Imagine we have a single event, which we will call E. The complement of this event, which we denote as E', represents everything in the sample space that is not in E if we take the set containing both E and E'. This set actually forms a perfect partition of our sample space, S. Let's verify this using the three rules we discussed in the previous slides. First, are they pairwise disjoint? Yes, because an outcome cannot simultaneously be an event E and not an event E in mathematical terms. The intersection of E and E' is equal to the empty set. Second, are they exhaustive? Yes, because by definition, every single outcome in our sample space must either fall into event E or fall into its complement, E'. Therefore, the union of E and E' equals the sample space, S. Finally, we must satisfy our third condition, non-zero probabilities. As long as the probability of event E is greater than 0 and less than 1, then both the event and its complement have a valid non-zero probability. This simple division of a space into what happens and what does not happen is the most fundamental type of partition you will encounter. Mathematical examples of partitions, continued. Now, let's move from the simple case of an event and its complement to something slightly more complex, the intersections of two events. Imagine we have two different events, let's call them E and F. While these two events might overlap, we can actually use them to slice our entire sample space into four distinct non-overlapping regions. This creates a perfect partition. Mathematically, we represent this set of four regions as E intersection F', E intersection F, E' intersection F, and finally, E' intersection F'. To make this more intuitive, let's break down what each of these four pieces actually represents in plain English. First, E intersection F' refers to all the outcomes that fall inside event E, but are not part of event F. Second, E intersection F represents the overlap, the outcomes that belong to both event E and event F simultaneously. Third, E' intersection F refers to the outcomes that are in event F, but are not in event E. And finally, E' intersection F' represents the outcomes that are outside of both events, meaning they belong to neither E nor F. By looking at it this way, we've taken two overlapping circles and identified every possible unique area, ensuring that every single outcome in our sample space is accounted for exactly once. This is a powerful way to visualize how complex events can be broken down into simpler, disjoint parts. Common mistakes to avoid. First, a very frequent mistake is confusing disjoint events with independent events. I see students mix these up all the time. Remember, when we say events are disjoint, we mean they are mutually exclusive. They simply cannot happen at the same time. In mathematical terms, the probability of the intersection of event I and event J equals 0. On the other hand, independent events are a completely different concept. Independence means that the occurrence of one event has no impact whatsoever on the probability of the other event occurring. They are not the same thing, so be careful with your terminology. Second, watch out for overlooking the exhaustive condition. It is easy to pick a set of events that don't overlap, but if you leave a gap, you haven't created a partition. For example, if you were looking at a standard deck of cards and you only listed hearts, diamonds, and clubs, you haven't partitioned the sample space. Why? Because you've left out the spades. A true partition must cover every single possible outcome in the sample space. Finally, don't ignore the probability condition. As we discussed in the earlier slides, every event in your partition must have a probability greater than 0. If an event is impossible, it cannot be part of a partition, especially when we start using these partitions in Bayes' theorem, where we often need to divide by these probabilities. As you know, division by 0 is undefined, so each slice of our sample space must be a possible outcome. Now, before we wrap up today's lesson, I want to pause and address some common pitfalls. As you move forward into more complex topics like Bayes' theorem, it is very easy to fall into a few specific traps, so let's look at what to avoid. Keep these 3 warnings in mind, and you'll be well on your way to mastering the next steps in probability. Key takeaways. To wrap up, remember that a partition is simply a way of dividing our entire sample space, which we call S, into several smaller events that are both mutually exclusive and collectively exhaustive. To ensure you have a valid partition, you must always check for these 3 mandatory rules that we discussed throughout the presentation. First, there must be no overlap. This means the events are pairwise disjoint, which we express mathematically as E sub I intersection E sub j equals the empty set. In other words, no 2 events can happen at the same time. Second, there must be no gaps. The events must be exhaustive, meaning the union of all our events, E sub 1 union E sub 2, all the fucking way through E sub n, must equal the entire sample space S. As we discussed with the cake analogy, the slices must perfectly reconstruct the original whole. And third, every event must be possible. We require that the probability of E sub I is strictly greater than 0. This is a vital technicality because, as we noted earlier, we cannot divide by 0 when we move into more complex calculations. Finally, please keep in mind that mastering the concept of partitions is not just an end in itself. It is the essential prerequisite for understanding the theorem of total probability and Bayes' theorem, which we will be tackling in our next session. All right, we have reached the end of our lesson, so let's bring everything together with a final summary of what we've learned today. Great job today, and I will see you in the next lesson.